Alright, so continue from the last video. We are going to look at the following two examples and see how we can apply the residue method to do the partial fraction decomposition. So let's look at the first example here. We have the numerator is 2x cubed minus 5x plus 2 all over the denominator x to the fourth power minus 20x plus 64. So let me just erase this for now because we probably need to use some of the space on the right hand side as well. And I'll write down the second problem later. So first, as we know, when we want to do partial fraction decomposition, we first want to figure out how to factorize the denominator. So in this case, we have x to the fourth power minus 20x squared plus 64. Notice that we can just treat x squared as our new variable, let's say y. So now we can just rewrite it as y squared minus 20y plus 64. Now doing the factorization, we get y minus 4 times y minus 16. So we can cross multiply and double check whether we get the coefficients in the middle or not. Then again, since y is actually x squared that we try to substitute, we now need to put it back to get the unique factorization, which is x plus 2 times x minus 2 times x minus 4 times x plus 4. Now I'm going to rearrange the order of the factors so that now we are going to write with an increasing order. X plus 4 times x plus 2 times x minus 2 times x minus 4, like this. Then for the numerator part, again, since we're trying to use the residue method to find out the partial fraction, we don't have to factor out anything in the numerator at all. And again, that's because when we try to write the partial, we're going to get the following. So we have x plus 4, x plus 2 here, x minus 2, and then x minus 4. Just like how we usually do partial fraction decomposition when we're using algebras. And now we just need to denote what are on top. So for the first one, we have the function with x equals negative 4, because this is the roots in the denominator here. So we get the similar expressions for the rest of the terms. Great. And here, recall that this f here is actually the same f as the given expression, because for all the denominators here, they're all linear terms, meaning the power is just the first power, not any higher powers that we need to manipulate with the residue, residue expressions before we try to figure out the values. So good. In this case, we can also just think that since we're doing the linear term, we can use the covering method to figure out each residue. So this implies that for the x plus 4 term, we are going to cover the x plus 4 in the denominator and then replace all the x's by negative 4. So I'm going to do the scratch work on the right hand side on top so that we once we get the value, we can put it back in. Great. So we get 2 times negative 4 cubed minus 5 times negative 4 plus 2 for the top part, all over the denominator, which gives us negative 4 plus 2, which is negative 2, times negative 4 minus minus 2 is negative 6. And for the last one, we get negative 8. So if we simplify it, we get, let's see, this is negative 4 to the third power is negative 64 times 2 is negative 128 plus 20 plus 2, so plus 28, which gives us negative 106. And divided by, well, we have 3 negatives down here, so we get negative, and then 2 times 6 is 12, 12 times 8 is 96. And if we simplify it, the negatives cancel out, and then on top we can divide by 2, and then on bottom we also divide by 2. We get 53 over 48. Great. So we can do the same thing for the other 3 different residues. So this is what we're going to get. The definition of residue. We have for the residue of the function with respect to -2, we get -16 plus 10 plus 2 all over. Now let's see, here we have -2 plus 4, which is 2. This term, the plus 2 term is cancelled out, so we move on to the next one. -2 minus 2, which is -4, and the last one we have -2 minus 4, which is -6. Then by simplifying, on top we have -4, on bottom we have, well, this. So during the cancellation we have -1 over 12. Good. Then for the third one, we now get 16 minus 10 plus 2 all over 6 times 4 times -2, which is going to give us 16 plus 2 is 18 minus is 8 over -48, which gives us -1 over 6. And lastly, we need to figure out the residue when x is equal to 4. We will get 128 minus 20 plus 2 all over 8 times 6 times 2, which gives us 110 over 96. And if we cross out or the 2, we'll get 110 over 96, and if we simplify it, we get 55 on top, 48 on bottom, meaning the residue here is 55 over 48. And that is it. We actually get our answers of this expression here using the residue method to do the partial fraction decomposition. Great. So we're going to move to the second example, which is even more complicated. Alright, here's the second example. We get the expression x squared minus 5x plus 4 all over the quantity x minus 2 cubed times x plus 3 squared plus x squared plus 4 times x squared plus 4. Then again, using the residue method, we're going to first break out the denominators. Now keep in mind, regularly when we write the partial fraction decomposition, we expect the denominator will be nice and neat, meaning we want to keep the coefficients in integers and also want to leave it in as real numbers. But when we use the residue method to help us finding the partial fraction decomposition, we cannot just simply keep what we expect regularly as our steps. Meaning, okay, so we'll get the following if we try to do a partial fraction decomposition, and of course, we don't know what the numerators are, meaning we actually need to find numerators, aka the leading the coefficients of each term. But there is one thing that we cannot really do when we have partial fraction decomposition using the residue method. When we do it with the residue method, we always want to keep in mind that we want to have some x plus something term in the denominator raised to some power, instead of having something such as x squared plus whatever or x cubed whatever. And the reason why is because again, the residue method, which is from the residue theory in complex analysis, is supposed to find out the we call the residue or the coefficients in the Laurent series, where each term in the Laurent series is actually is involving with the with only one x solution. So in other words, we want to factor out so that in the denominator there's only one x values that that is going to make it into 0, and that x value could be real number, but of course could also be an complex number. So in this case, all the terms up to here are fine. That we only have one x values causing the denominator being 0. However, in the last term, we have x squared plus 4 equals 0 if and only if x is equal to plus or minus 2i. And perhaps you might think, well, in this case, isn't that great? There's no real numbers. But again, when we use the residue method, we can also use it with complex numbers. And now we see that there are two different complex solutions that can make the denominator here, x squared plus 4 equals 0. So what we need to do here is now we need to break this, the last fraction, into two parts. We now need to break it into x plus 2i and x minus 2i. Let me write in red. So that now each term has only one value, making the denominator equal to 0. So after having this set up, we are actually ready to figure out the residue value, or simply call the residue of each term, to find out what the final answer is for the partial fraction decomposition of the expression that we have. So first, let's denote how we write the residue using the general expression, which is a to something comma something. So here we will get a to 2 comma 1, and we have a 2 comma 2, a 2 comma 3. So similarly, we get a negative 3 comma 1 and a negative 3 comma 2 right here. And last but not least, we have, well, in this case, since these two are just linear terms in the denominator, we can just simply write as the residues of the original function. Let's call it f here, for x equals negative 2i. And then for the last one, we get residue of the function when x is equal to positive 2i. Good. So perhaps you may wonder how we can find out these values here. Again, we can just use the general result from the previous video to substitute into the general formula, so that we will be able to get the residue. And because the process is very long and tedious, I'm just going to write out the answers for each one and let you guys check the answers by yourself. So we will actually get the following. For a2 comma 1, we get this expression here, or this value. We'll get this value here, 685 over 1,285,029. And then for a22, we get 9 over 1,000. For a23, we get 1 over 196. For a negative 3 comma 1, we get negative 199 over 16,875. For a minus 3 comma 2, we get negative 28 over 1,625. Now, last but not least, for the residues that involved with the complex numbers, we get the following. For negative 2i term, we get 5. Let me rewrite this. We get 5 over 32 times 7 plus 17i. Where the positive 2i term, we get 5 over 32 times 7 minus 17i. Nice. But of course, it's not over yet. If we're thinking the expression needs to be written in only real numbers, and in particular integer coefficients, because again, for the last two terms, it's supposed to be written in something over x squared plus 4. But now, using the residue method, we decide to break it into two partial fractions, that each part has a denominator involving with the imaginary unit I. So last but not least, we need to combine these two back. And of course, we know that these two terms, their common denominator would just be x squared plus 4, which is how we break it into two parts. So nice, we actually get the denominator quickly. Now, for the numerator parts, again, we just need to do the cross multiplication. So again, I'll let you guys check the answer by yourself, but this is what we get after we cross multiply and simplify. We will get 5 over 5,408 times the quantity, the quantity 7x minus 34. And that is our final answer. Again, this is just for the other way around. This plus sign right here is just for these two parts, and then you just need to copy the rest to finish up your solutions. Alright, pretty cool, huh? So if you have any thoughts or ideas, please leave your comments below. And if you didn't watch the first two parts about the ideas that used in this video yet, go and check it out. I'll put the links below. And if you want to watch more of my videos, don't forget to subscribe so that you can check out my channel and find out more of my videos. And that's it. I'll see you next time.